Hello everyone. Declaration 1. The copyright of this article or video belongs to the original author Da Wang. 2. The content of this article shall not be reproduced without the permission of the original author. Otherwise, it will be regarded as infringement. 3. Reprint or quote the content of this article. Please indicate the source and the original author. 4. For non-compliance with this statement or other illegal use of the content of this article, I reserve the right to pursue according to law. 5. The Chinese version of this paper has been uploaded to the internet, entitled 四色猜想的证明, which can be used as a reference for this paper. Chapter 3. The invalidity of Rodley's cycle model. Section 3.1. How to obtain Rodley's cycle model. Definition 52. A single OD sufficient graph G1 has an origin-related cycle XH1, and if XH1 is not a Rod cycle, then XH1 is called a Rodley's cycle of G1, as shown in figure 49 and figure 50. In figure 49, the origin-related cycle is from one ring, the OD, which arrow points is the front OD of the action ring of the corresponding number, to 8 ring. In figure 50, the origin-related cycle is from 1 to 8 rings. So, for example, in figure 49, the first action ring is 1, this one, and the second is this one, and the third is this one, and so on. Law 9. A single OD sufficient graph G1 has an origin-related cycle XH0. If the OD bridge structures of XH0, such as JG1, JG2, etc., have both spiral rod structure and a straight rod structure, it is possible to make these straight rod structures, such as JG1, no longer than the OD bridge structures by merging the sequential action rings into one action ring, which makes all the remaining OD bridge structures, such as JG2, to be spiral rod structure. The model XH1 got from the operation above is called the Rodley's simplified cycle model of XH0, in short, Rodley's cycle model. In figure 51, 1-1, 1-2, 1-3 can be combined into a ring 1 due their sequential order in action process. And the same situation occurs in 2-1 and 2-2 rings combined into ring 2. 3-1 and 3-2 combined into ring 3, resulting in the model of figure 52. In figure 52, there is only one department, and all the ODs in the department are part of the spiral rod structure. So we can see In figure 51, this 2-1 and 2-2 combined to the OD ring 2. And 1-1, 1-2, 1-3 combined to OD ring 1. Section 3.2 Proof of the widespread invalidity of roadless cycle models. Definition 54. X1, X2, and so on are the departments of cycle XH1. Extract two constituent rings, e.g., xm-1 and xm-2. xm-1, xm-2 is called ring pair of the department xm. From each of these departments, e.g. xm, to form a set S1. S1 is called ring pair set of XH1. If S1 contains the ring pairs of all departments of XH1, S1 is called the all department ring pair set of XH1. Definition 55. HH1 has a ring pair set HDJ1 if any two ring pairs such as XM1-1, XM1-2, and XM2-1, XM2-2 ring pairs of HDJ1 all meet the following conditions. HDJ1 is called the sequential overlapping set of XH1. 1. XM1-1, XM1-2 belongs to department XM1. XM2-1, XM2-2 belongs to the department XM2. 2. The order of action of the constituent rings of XM1-1, XM1-2, and XM2-1, XM2-2 is in XH1 is alternately arranged according to the department. For example, XM1-1 happened first, then XM2-1 happened, and then XM1-2 and XM2-2, and go back to XM1-1, or XM1-1, then XM2-2, XM1-2, XM2-1, and then go back to XM1-1. The set here or here in figure 49 and here in figure 50 are the sequential overlapping sets of the cycle models in these figures. Note, unless otherwise specified, all the action rings represented by xm-n in this paper represents the n number action rings of the M department. Definition 56. There are two sets of ring pairs, x1-1, x1-2, and x2-1, x2-2 in the cycle model XH1. The action times of the constituent rings of these two sets of ring pairs in XH1 are not alternating based on the department in which they are located. So these two ring pairs are each other's uneven ring pairs. Definition 57. The roadless cycle model XH1 has a sequential overlapping set HDJ1. The departments of the ring pairs in HDJ1 form a closed ring structure through the connection relation of the origin bridge structure, referred to as the origin connection relation. Then HDJ1 is called the set of sequential overlapping closed ring pairs of XH1, abbreviated as time overlapping closed set. Definition 58. A time overlapping set in which the relative orders of ring pairs is consistent with the origin connection of the departments is called a standard time overlapping closed set. For example, there is a ring pair set HDJ1 equals this. The action sequence of the rings of the 4 ring pairs in HDJ1 is this: 1 1, 2 1, 3 1, 4 1, 1 2, 2 2, 3 2, 4 2. The origin connection relationship between the X1 to X4 series is 1 connects 2, 2 connects 3, 3 to 4, 4 to 1. HDJ1 is a standard time overlapping closed set. Definition 59. A time overlapping closed set that is not a standard time overlapping set is called a non-standard time overlapping closed set. For example, there's a ring pair set HDJ1 equals this. The action sequence of the rings of the 4 ring pairs in HDJ1 is 1 1 to 2 1 to 3 1 to 4 1 to 1 2 2 2 3 2 4 2. The origin connection relationship between the X1 to X4 series is 1 to 3, 3 to 2, 2 to 4, 4 to 1. HDJ1 is a non-standard time overlapping closed set. Definition 60. In the single OD sufficient graph G1, the Rhodley cycle model XH1 exists when only the state cycle of the OD bridge structure is considered. XH1 is called the origin bridge structure Sloot cycle model, origin Sloot model for short. Figure 49 and Figure 74, 75, Figure 76, Figure 77, and so on in Appendix 4 are the origin Sloot models. We can first to see 49. Okay, we can see Figure 49. This cycle makes sure the OD, the origin bridge point, have a sloot, in the cycle process. We can see this bridge structure, origin bridge structure. So first we go here. this ring act first, and this ring act second, and this ring act third, and this ring act fourth. So for this GG1, the whole action process and the action rings concerned satisfies the existence requirement of GG1. So for the rest of the OD origin bridge structure, the cycle process all satisfy them. Yeah. So same is happened to figure 50 and these figures in appendix 4. You can see this figure, you can see OD bridge structure here, and so on, and so on. The action process all satisfies their requirement of existence. So same to this figure, maybe this figure. Oh, yeah. This. Definition System 1. Consider the departments such as x1, x2 in the origin slot model as points. Consider the origin connection relationship of the points outlined. The formed single chain or single chain ring relationship lambda is called the sympath. Definition 62. For the non-origin slot model XH1, if there is an origin slot model XH1M, that meets the following conditions, then the following definitions exist. 1. The total number of the departments in XH1M, M here, is same as that in XH1. 2. There are ring pair set HDJ1 equals this, and the same pairs lambda of XH1. 3. XH1M has a ring pair set HDJ1M. HDJ1M equals this. 4. There is a 1-to-1 correspondence F1 between the departments of HDJ1M and the departments of HDJ1, such as X1M in HDJ1M and X1 in HDJ1. 5. Let the two departments of F1 relationship be XPM and XP. There is also a one-to-one correspondence F2 between the rings, the two rings here, of XPM in HDJ1M and the rings here of XP in HDJ1. 6. Let the relative sequence of action of the ring in HDJ1 in XH1 be nu. The relative sequence of action of the ring in HDJ1M in XH1M be nu apostrophe if the rings in nu apostrophe is replaced according to the F2 relation. The relative sequence of the ring action obtained is nu. 7. The same path lambda in XH1 still exists between departments corresponding to F1 relations in XH1M, as defined below. 1. XKM-1 or SKM-2 and XK-1 or XK-2 corresponding to F2 are mutually matching rings. 2. XKM and XK corresponding of F1 are mutually matching departments. 3. XH1M is called the matching origin-slot model of XH1 with respect to HDJ1 and lambda. Definition 66. For the non-origin-slot model XH1, the matching origin-slot model, such as XH1M with the fewest component action rings, is called the fewest processing ring matching origin-slot model, referred to as the minimum matching model of XH1. Definition 63a. XH1S is the matching origin-slot model of XH1 with respect to HDJ1. The one-to-one correspondence between the department in XH1 and its matching department in XH1S is Fs. The same path lambda exists in XH1. Same path lambda s exists in XH1S. If all the constituent departments of lambda s are replaced by the departments in XH1 by Fs, the resulting same path is lambda. Then lambda is called the same path constraint of XH1S with respect to HDJ1. Path constraint for short. Law 10. Any origin-slot model XH1 has a minimum matching model of XH1, e.g., XH1M constrained by any set of ring pairs, e.g., HDJ1 and the same path, e.g., lambda, of XH1, and any one of these minimum matching models, such as XH1M, has the following properties. In any department of XH1M, such as XKM, there is a ring pair such as HDKM, XKM-1, XKM-2. HDKM exists in a standard time overlapping closed set S1 of XH1M. See Appendix 4 and Appendix 5 for specific cases. The lambda constraint condition in Appendix 4 is a non-set. Appendix 5 gives the case of matching a origin-salute model satisfying thin path constraint, and gives the case of method of obtaining the matching origin-salute model. Appendix 4. Case 1 of Law 10. Case 1. Definition 66. Rodley cycle model XH1 has a whole all department ring pair set HDG1, which satisfies the following properties. 1. There are two matrices M-1 and M-2, and the time T0 during X1 process. 2. All the first action rings of the ring pair of HDG1 which act after T0 are located in M-1, and all the second ones are located inside M-2. 3. The action time of any action ring in M-1 with respect to T0 is earlier than that of any action rings in M-2. 4. The left action ring of the M-1 or M-2 acts earlier with respect to T0 than the action ring, than the right action ring of the M-1 or M-2 in the same line. 5. The upper action ring of the M-1 or M-2 acts earlier with respect to T0 than the lower action ring of the M-1 or M-2 in the same column. 6. All same department rings in HDG1 are located in the same positions as M-1 and M-2. Such HDG1 is the standard sequential uneven ring pair set of XH1. This set, called the standard uneven matrices set of XH1 with respect to HDG1. T0 is called the boundary time of this set. The set S1, this, is the standard uneven matrices that of the matrices set of the Rodley cycle model XH1 apostrophe with respect to HDG1 apostrophe. The internal values of M apostrophe dash 1 and M apostrophe dash 2 are shown in the following tables. HDG1 apostrophe is the standard sequential uneven ring pair set of XH1 apostrophe. HDG1 apostrophe equals this. The relative order of the action time of the HDG1 apostrophe action rings in XH1 apostrophe is arranged according to the number from smallest to largest. Note, unless otherwise specified, the order of action of all action rings in the cycle model in which they are located follows this arrangement rule. And the action time of the 21 action ring is adjacent to that of the 1 action ring. The moment T apostrophe 0, when the 20 action ring ends and the 21 action ring is about to act is the boundary time of S1. As shown in figure 75, through the addition of 9, 10, and 11 action rings, the matching model x1 xh1 of xh1 apostrophe with respect to hdj1 apostrophe is obtained. The path constraint of xh1 with respect to hdj1 apostrophe is non-set. The matching department of xpq of xh1 apostrophe in xh1 is xpq, and the matching ring of M action ring of xh1 apostrophe in xh1 is M action ring. In any department, such as xk of xh1, there is a ring pair, such as hdk xk-1 sk-2. hdk exists in a standard time overlapping closed set S1 of xh1. If there is no special explanation, the matching relationship and the time overlapping closed relationship above still exists on the cases with the same name in all appendixes in this paper. So we can check figure 75. Yeah, figure 75 with the matrix here. And in the matrix, there's no 9, 10, and 11 action rings. So the 9, 10, and 11. So the 9, 10, and 11 ring, when they add to the matrices and finally got the origin salute cycle process, which make all the origin bridge structure exists, meet the structure's requirement to exist. Case 2, definition 65. All departments ring pair set hdj1 apostrophe of the Rodley cycle model xh1 apostrophe, there is no standard uneven matrix set S1. Then hdj1 apostrophe is the non-standard sequential uneven ring pair set of xh1 apostrophe. Suppose there is a Rodley's cycle model xh1 apostrophe who has an all departments ring pair set HDJ1 apostrophe here. The ring action order of XH1 apostrophe follows the natural number order, with 5A between 5 and 6, and 31 between 30 and 13A between 13 and 14. Here, HDG1 apostrophe is the non-standard sequential and even ring pair set of XH1 apostrophe. Figure 76 shows the ring action process of XH1 apostrophe, which is the matching Regensloot model XH1. The ring action order of XH1 follows the natural number order, with 5A between 5 and 6 and 13A between 13 and 14. Case 3. Rodley cycle model XH1 apostrophe has all departments ring pair set HDJ1 apostrophe here. Unlike the previous two cases, it is not possible to separate the two rings of all ring pair in HDJ1 apostrophe with two time points during the XH1 apostrophe cycle, as shown in figure 77. With the participation of 1, 4, and 7 action rings, the Rodley cycle model XH1 exists. XH1 is the matching Regensloot model of XH1 apostrophe with respect to HDJ1 apostrophe, and it is also the minimum matching model of XH1 apostrophe with respect to HDJ1 apostrophe. Appendix 5, Case 2 of Law 10. There exists the Regensloot model XH1 apostrophe. XH1 apostrophe has an all departments ring pair set HDJ1 apostrophe here. There is a path constraint lambda. X1 connects X4 in XH1 apostrophe. Figure 78 shows matching Regensloot model XH1 of XH1 apostrophe with respect to HDJ1 apostrophe. XH1 satisfies the path constraint lambda. The matching department of Xn of XH1 apostrophe in XH1 is Xn, and the matching ring of n action ring of XH1 apostrophe in XH1 is M. And the matching ring of M action ring of XH1 apostrophe in XH1 is M. Figure 79 shows matching Regensloot model XH2 of XH1 apostrophe with respect to HDJ1 apostrophe. XH2 does not satisfy the path constraint lambda. The matching department of Xn of XH1 apostrophe in XH2 is Xn, and the matching ring of M action ring of XH1 apostrophe in XH2 is M. Similarly to all cases in Appendix 4, in any department such as xk of XH1 or XH2, there is a ring pair such as HDK, SK-1, SK-2. HDK exists in a standard time overlapping closed set S1 of XH1 or XH2. Definition 66. The loop sequence XL1 is obtained by ordering the action rings in the ring pair set HDG1 according to their action time in the cycle. Divide XL1 into several sub-processes, XL1-1, XL1-2, and so on. Each subsequence, e.g., XL1-M, does not contain two action rings of one department. Set eta as the grouping method with the least number of groups. Let the time between adjacent subsequences of eta, e.g., XL1-1, XL1-M, XL1-M add 1, B, Tm, and Tm is called the gap time of least mutually different department ring process of eta. The set S1 of all gap times of least mutually different department ring process of eta is called the least mutually different department ring process time point set. In short, least time point set. In the following two figures, the same number in each figure represents the ring action in the same department, and the arrow represents the sequence relationship between action rings. The set, this, in figure 80, is a least time point set of the ring pair set. The set, this, in figure 81 is not the least time point set of the ring pair set because the number of corresponding group is not the least. One drawing method of the minimum matching model. Method 3. 1. Arrange action rings in the corresponding period of elements, e.g., T1 of the least time point set, e.g., S1, and obtain the minimum matching model, e.g., XH11 of the known origin slot model, e.g., XH1, with respect to one of XH1's all departments ring pair set, e.g., HDG1. 2. Modify XH11 to satisfy the XH1 same pair constraint, e.g. lambda. For example, in case 1 of appendix 4, there is XH1 as shown in figure 75, and XH1 is the minimum matching model of XH1 apostrophe with respect to HDG1 apostrophe. It is known that XH1 apostrophe has a same path constraint lambda. X apostrophe 1, 2 to lambda. Connected to X apostrophe 2, 3. By modifying XH1 according to lambda, the Rodley cycle model X H lambda, as shown in figure 82, is obtained. XH lambda is the matching model of XH1 apostrophe with respect to HDG1 apostrophe that satisfies lambda. Definition 64. There is an origin solution model XH1 and XH11 and 2 are the matching origin-solute models of XH1. If XH11 and XH12 meet the following conditions, then they are each other's common order matching origin-solute models, referred to as common order models about XH1. Otherwise, they are strange order models. 1. To any department of XH1, such as XM, there is a matching department XM1 in XH11, and also there is a matching department XM2 in XH12. XM1 and XM2 meet the following conditions. The following definitions exist. A. XM1 and XM2 are dual matching departments of each other with respect to XH1. B. The numbers of action rings in XM1 and XM2 are the same. C. There is a one-to-one correspondence Fm between the action ring in XM1 and the action ring of XM2. For example, the XM1-1 action ring corresponds to the XM2-1 action ring, and Fm is called department ring relationship of double matched model of XM1 and XM2. D. The sum of the ring relations F, capital F, between all the dual matching departments of XH11 and XH12 about XH1 is called the double matched model ring relation of XH11 and XH12. 2. Capital F meets the following conditions. 1. Let the relative timing relationship of each action ring in the XH11 process be nu1. B. Let the relative timing relationship of each action ring in the XH12 process be nu2. C. If replace all the action rings in nu1 according to the capital F relation, and the relative timing relationship obtained will be nu2. Definition 65. It is known that there is an origin-solute model XH1. There is a matching origin-solute model XH11 of XH1. Let the one-to-one correspondence between the department in XH1 and its matching department in XH11 be F. X1 is the department in XH1, and the matching department of X1 with respect to F is X11. If XH11 meets the following conditions, then XH11 is called the standard time overlapping closed common pattern matching origin-solute model. Time overlapping closed matching model for short of XH1 with respect to X1. 1. XH1 has a standard time overlapping closed set S1, which includes a ring pair of X1. The origin connection relationship of S1, which makes S1 standard time overlapping closed set, is lambda 1. XH11 has a standard time overlapping closed set S1 apostrophe, which includes a ring pair of X11. Two. Each of S1 and S1 apostrophe has the same number of departments whose ring pair is located in S1 or S1 apostrophe. 3. For the department such as Xm, in which any ring pair in S1 resides, there is a department Xm1 in X1 XH11. Xm1 is the matching department of Xm, and there is a ring pair in S1 apostrophe resides in Xm1. There is a one-to-one correspondence Fm between the action ring of Xm located in S1 and the action ring in Xm1 located in S1 apostrophe. For example, Xm-1 corresponds to Xm1-1. Such a sum of correspondence between all rings of S1 and all rings of S1 apostrophe is capital F. 4. Let the relative time sequence of all acting rings in S1 be nu1, and the relative timing relationship of all action rings, this is action, all action rings in S1 apostrophe be nu1 apostrophe. If we replace all the action rings of nu1 apostrophe according to capital F, the resulting relative timing relationship will be nu1. 5. There is the origin connection relationship lambda 1 apostrophe of S1 apostrophe in XH11. If all departments in lambda 1 apostrophe are replaced by the ones in XH1 according to F, the obtained origin connection relationship will be lambda 1. Law 11. It is known that there exists an origin solute model XH1, and X1 is a department of XH1. If the following conditions are true, then the following conclusions are also true. Conditions. 1. There are several all departments ring pair set. This of XH1. 2. There are several syn passes, lambda 1, lambda 2, and so on to lambda q of X1 in XH1. 3. There are several matching models, XH11, XH12, and so on to XH1m of XH1. Any matching model, such as XH1s, meets the following conditions. A. XH1s is the matching model of XH1 with respect to HD JK2, and the one-to-one correspondence between the departments in XH1 and its matching department in XH1s is Fs. B. There is a lambda k1. Lambda k1 is the path constraint of XH1s with respect to HDJ-K2. C. XH1s is the origin solute model that satisfies condition A, B, and contains the least number of action rings. 4. In XH11, XH12, and so on to XH1m, there is no time overlapping closed matching model of XH1 with respect to X1. Conclusions. There is a matching model XH1m at 1 of XH1, XH1m at 1, and any one of XH11, XH12, and so on to XH1m are strange order models to each other. XH1m at 1 is also the origin solute model, which meets one of the following conditions with the least number of action rings. 1. There are lambda k1 and HDJ-K2. XH1m at 1 is the matching model of XH1 with respect to HDJ-K2. Lambda k1 is the path constraint of XH1m at 1 with respect to HDJ-K2. 2. there are lambda k1 and new all departments ring pair set HDJ P at 1. X H1M at 1 is matching model of XH1 with respect to HDJ P at 1. Lambda K1 is the path constraint of XHM at 1 with respect to HDJP at 1. 3. There are new thin paths lambda Q at 1 of X1 in XH1 and HDJ K2. XH1M at 1 is the matching model of XH1 with respect to HDJ K2. Lambda Q at 1 is the path constraint of XH1M at 1 with respect to HDJ K2. There are new thin paths lambda Q at 1 of X1 in XH1 and the new all departments ring pair set HDJ P at 1. XH1M at 1 is the matching model of XH1 with respect to HDJ P at 1. Lambda Q at 1 is the path constraint of XH1M at 1 with respect to HDJ P at 1. Theorem 14. If law 11 holds, then all departments, e.g. x1 of any roadless cycle model XH1 exist in a standard overlapping closed set in which x1's ring pair locates. Proof. If this theorem is not true, then XH1 exists a department x1 and there is no standard time overlapping closed set in which x1's ring pair locates. That is, there is no time overlapping closed matching model of XH1 of x1. Then, according to law 11, the minimum matching model XH1M at 1 of XH1 can be obtained, and XH1M at 1 and any one of non-minimum matching model XH11, XH12, and so on to XH1M of XH1 are string order models of each other. By analogy, XH1 will have an infinite number of minimum matching models, and any two of these minimum matching models are string order models of each other. According to the definition of the string order model and the definition of the minimum matching model, we can see that there are infinite acting rings in XH1. Well, the number of action rings in any roadless cycle model is finite. Therefore, if the hypothesis is not true, the theorem is true, QED. Therefore, the hypothesis is not true, so the theorem is true, QED. Definition 66. There is a roadless cycle model XH1, where X1 is a department of XH1. The following is a method for determining the standard time overlapping closed set where the ring pair of X1 is located. Method 2. 1. Determine the time overlapping set where the ring pair of X1 is located. 2. Based on the original connection relationship of XH1, from less to more, try to obtain the standard time overlapping closed set where the ring pair of X1 is located from the set in 1. Law 12. Due to the universal existence of the structure of the time overlapping closed set, the roadless cycle model, except for the finite times, can't be established because of the interaction between the interaction rings, as shown in figure 53. There is an origin-slot cycle model XH1 consisting of two departments, X1 and X2, and the action rings of XH1 act in order of labels from 1 to 6. Due to the existence of structures or time overlapping closed set, such as this and this, there are intersection points K and 2, K1 and K2 of X1 and X2. There exists the structure JGK1 or JGK2, which just consists of a single point K1 or K2. The state cycle of age continuous structure JGK1 apostrophe or JGK2 apostrophe of JGK1 or JGK2 can't exist in XH1. Therefore, the origin-slot cycle XH1 can't be established. So we can see in figure 53, K1 points here, K2 points here. So we can see the K1 structure state change is changed by ring 1, ring 5, ring 6, and ring 2. Okay. After the ring 1 act, the ring 2 broke ring 1, and the ring 5 act before ring 6. So after ring 2 act, the next state change is caused by ring 5. But ring 5 is broken by ring 2 here. So ring 5 can't act. So the structure K1 can't be established. The same condition happened to this K2. Chapter 4, the final proof of the four-color conjecture. Theorem 15. If law 8 holds, any straight rod graph such as G1 has four-color slot graph. Proof. The premise of the theorem is the premise of law 8. According to law 8, if G1 does not have an OD ray string, there is an infinitely long action process, GC1. And any two states, ZT1 and ZT2 in GC1, are not the same. Given the finite number of states of figure G1, such a GC1 does not exist. So G1 must be able to obtain a bridge chain of its unique OD through an origin-related process. By now, G1 satisfies the condition of theorem 4, and G1 has four-color slot graph, QED. Law 13. If single OD sufficient graph G1 is a spiral rod graph, there is a transfer method eta of a region-related process. If there is any region-related process GC0 obtained by eta starting from ZT0 and GC0 has the following properties. 1. There are n-initial action rings in GC0. 2. Any state in GC0 does not contain the origin-region bridge chain. 3. Any two states in GC0 are different. Then there is another origin-related process, GC initial from ZT0 obtained by eta, which has the following properties. 1. There are n apostrophe initial acting rings in the GC1 in the GC initial. N apostrophe initial is greater than n initial. 2. One of the following properties is true. A. The state ZT initial exists in GC initial, and the origin bridge chain exists in ZT initial. B. All states in the GC initial, such as ZTK, do not contain the origin bridge chain, and neither of the two states in the GC initial is the same. Theorem 16. If law 13 holds, then all single OD sufficient graphs G1 has four-color absolute graph. Proof. If this theorem is not true, that is, there is a single OD. There is a single OD sufficient graph G1 without four-color absolute graph. For any origin-related process acting on G1, such as GC1, there is no origin bridge chain in any of its states. Otherwise, by theorem 4, G1 has a four-color absolute graph. According to law 13, there is a transfer method eta, which allows the number of states of G1 to increase unidirectionally before the four-color absolute graph is obtained. That is, G1 can get an infinite number of states by eta. However, the number of states obtained from G1 under the operation of a region-related process is limited. Therefore, the hypothesis is not valid. That is, the theorem holds QED. Theorem 17. Any spherical graph, e.g. G1, has a four-color absolute graph. Proof. For a color block graph, G1 with multi-connected countries, define the spherical connecting map. G1 can be divided into several maps with only simple connected countries, G1-1, G1-2, as shown in the following figure. As long as each split graph, figure 54, individual gray areas and points of neighboring countries, countries 1, G1-M, e.g., has a four-color absolute graph, G1-M apostrophe. G1 has a four-color absolute graph. Okay, so this okay. this graph is separated in this way. For a map G1 containing only simple connected countries, as the introduction says, the countries in G1 can be turned into points and the common borders between countries can be turned into lines, so that we can obtain the point graph G1S of G1. If G1S has a four-color solute graph G1S apostrophe, then the value of each point in G1S apostrophe can be assigned to the corresponding country in G1, and the four-color solute graph G1 apostrophe property 1 of G1 is obtained. Let's assume that between any 2 points of G1S, such as K1, K2, there is a chain L connecting K1 and K2. That is, K1 communicates with K2, condition 1. Then, according to the definition of spherical graph, there are operation methods eta, sequence XL1 and sequence XL2, which satisfy the following properties. A. XL1 is a sequence this of graph. B. The n in A is number of points in G1S. C. In XL1, Gm at 1s is obtained from GMS by eta operation. D. Specific operation requirements of eta. 1. Combine a pair of points alpha 1, alpha 2 with a connection into a single point alpha. 2. The connecting points of alpha 1 and alpha 2 in the GMS connect to alpha at Gm at 1s. 3. Any 2 points such as K1 apostrophe and K2 apostrophe in the GMS of 2 communicate with each other, and there are no multi-connected points. Point K3 apostrophe e.g. it has other points K5 apostrophe, K6 apostrophe, and so on of the graph both inside and outside of it. E. XL2 this is the reverse sequence of XL1. F. In XL2, if G m at 1s has a four-color solute graph G m at 1s apostrophe, then GMS must also have a four-color solute graph GMS apostrophe. Here's why. 1. Let a point alpha of Gm at 1s split into 2 connecting points alpha 1 and alpha 2 of GMS. 2. Assign the values of all points in Gm at 1s apostrophe to the corresponding points in GMS, and assign the values of alpha to alpha 1 and alpha 2. The single OD assigned graph GMSF is obtained. 3. There is a single OD sufficient graph of GMSF called GMSF apostrophe. By theorem 16, there exists the four-color solute graph GMSF2 apostrophe of GMSF apostrophe. By theorem 1, there exists four-color solute graph of GMSF called GMS apostrophe, that is, F holes. Since GNS in XL2 has a four-color absolute graph GNS apostrophe. By F, all elements in XL2 have a four-color absolute graph. Therefore, G1S has a four-color absolute graph G1S apostrophe. By property 1, G1 has a four-color absolute graph G1 apostrophe. If there are 2 points such as K1 and K2 in G1S and K1 does not communicate with K2, G1S can be divided into several graphs satisfying condition 1 and assigned separately. Therefore, in this case, G1 still has a four-color absolute graph. In summary, theorem 17 is true. QED. Finally, we check the case of law 11, appendix 6. It is known that there exists an origin absolute model XH1 apostrophe, and X2 is a department of XH1 apostrophe. The following conditions exist. 1. There is an all departments ring pair set HDJ1 apostrophe here of XH1 apostrophe. 2. There is a sine path lambda 1 of X2 in XH1. 3. There is a matching method XH2 in figure 79 of XH1 apostrophe. XH2 meets the following conditions. A. XH2 is the matching model of XH1 apostrophe with respect to HDJ1 apostrophe. B. There is lambda 1. Lambda 1 is the path constraint of XH1 with respect to HDJ1 apostrophe. C. XH2 is the origin absolute model that satisfies condition A, B, and contains the fewest action rings. 4. XH2 is not the time overlapping closed matching model of XH1 apostrophe with respect to department. Department X2. Under the above conditions, there is a matching model XH3 of XH1 as shown in figure 83. XH3 and XH2 are each other's strange order models with respect to XH1. XH3 is also the origin absolute model with the fewest action rings, satisfying the following conditions. There are new XH1 apostrophe sine path lambda 2. X2 connects to X4 of X2 and HDJ1 apostrophe. XH3 is the matching model of XH1 apostrophe with respect to HDJ1 apostrophe. Lambda 2 is the path constraint of XH3 with respect to HDJ1 apostrophe. So here is the reference.